Hi guys. So pretty much everything on this thermodynamics lesson is going to be review. There's one little concept that we didn't cover in first semester called enthalpy of formation. It's going to be the first one that we'll see. It's pretty straightforward. The reason we didn't cover it first semester was because in the AP chemistry teacher community, there's been some debate about whether or not it's going to show up on the test or not. And originally, everybody had kind of assumed that it wasn't going to based on some things that were said. And then now, I don't know, let's just say we've gotten a little worried that it might show up. So it's a pretty simple concept, pretty straightforward concept. So I'm just going to go ahead and teach you how to do it. What you see up on your screen right now is just, thermodynamics in general, some basic laws. So we've covered these before. The first law of thermodynamics is that energy can't be created or destroyed. Second law of thermodynamics is that if a reaction is spontaneous written in one direction, then it won't be spontaneous in the reverse direction. And that makes sense. I mean, if two things react, they're going to form products. They won't be spontaneous in the other direction. And remember, spontaneous means to form more products than reactants were there. So your K value, remember that K we've been calculating, is greater than 1 because you have a higher concentration of products than reactants. State function we discussed as well back when we did thermo the first time. It's a value that only depends on how what the initial value is and what the final value is, not on how you get there. Okay, not the path by which you travel. And enthalpy, entropy, and free energy, all the things that we're talking about today are all state functions. Essentially what that means to us in here is that there are a lot of ways that we can solve the exact same problems. Okay, so if you remember with delta H, we learned a couple of different ways to calculate delta H. We're going to review those today. And then you'll see with entropy and free energy that there's multiple ways to calculate them. And as long as you're using valid information and based on the exact same initial and ending points, then any method you use is fine. The other thing that's on this one is what standard state means. What we're going to see a lot of, especially in this part of thermo, is it won't just say delta H. It'll have a little degree symbol on there, or delta S will have a little degree symbol. All that degree symbol means is standard state. Okay, and standard state is defined as the pressure is at 1 atm. The liquids and solids that we have are all pure, which is kind of pointless because we always deal with that, but the liquids and solids are pure. And then this is an important one. All the solution molarities are 1. Okay, so all the concentrations of the solutions are 1. Temperature is 298. And those are standard state conditions. So you definitely want to learn those. You definitely want to learn what situations we're looking at when we do see this little degree symbol on things. Also, we're going to be studying this enthalpy of formation. Okay, delta, I don't know what happened on my copying. There should be a delta there. Delta HF is something called enthalpy of formation. We'll see it here in a second. And essentially, it's a value that represents how much energy was given off when a certain compound was made from its elements. And so if you take a look here, this says the energy of formation of an element. Okay, so a pure element, like zinc, magnesium, oxygen, any of those pure elements. Well, they're not compounds. And since they're not compounds, they were never formed from other elements. And since they were not formed from other elements, their delta HF will be 0. So anytime you have a pure element for enthalpy of formation, you're going to use a value of 0. That's definitely something they like to ask about. They like to ask, give you a list. Which of the following has an enthalpy of formation of 0? And they'll list a whole bunch of compounds, and then there'll be one element by itself. And the element is the 1. All right, so let's take a little bit closer look at this enthalpy of formation. First of all, just a quick reminder on what enthalpy is. Enthalpy is a measurement of the energy that's either absorbed or released when a bond is formed or broken. And we're going to get back into bond energy here in just a minute. If you remember, we did calculate it that way using natural bond energies. But this is a slightly different way to do it. And again, as long as you are looking at the same reaction, we can use a variety of ways. A quick little reminder about endothermic, exothermic. Exothermic's a negative delta H, and endothermic is a positive delta H. These signs are extremely important. So if you don't remember those, make sure you make yourself a note because you have to understand the signage on what we're going to be doing with this thermodynamics. Whether or not it's positive or negative is extremely important. All right, heat of formation, like we were just saying, it's a change in energy when a compound is formed from its component elements. Okay, so a compound is formed from its component elements. And then a delta HF for any pure element then has to be 0 because an element can't be formed from its elements. These are values that are given on a table. There's a big table with all the enthalpies of formation of pretty much every single compound you could possibly imagine, okay? And that's what this note is saying right here, is you would have to be given these delta HF values to use the equation we're about to look at. So we can calculate the change in enthalpy for an overall reaction if we take all of the product enthalpies of formation and we subtract them from all the reactant enthalpies of formation. And again, all of this data that would be here comes from a table. So we just take all of the enthalpies of formations for all the products minus all the reactants, and voila, you have the overall change in enthalpy for the whole reaction. And again, these enthalpies of formation have to do with when that compound is made from elements, and in the equation it might not be being made from elements, but regardless of how it's made, it still releases or absorbs the same amount of energy because it's a certain compound. So it can be used because of the whole idea of state function. Let me show you what it looks like. So we have this practice problem. Because you don't have a table accessible, to you right at this moment, I've put the values within the problem. So they give you the balanced equation. You see the balanced equation, and then they tell you if the delta HF for CH3OH is this, delta HF for CO2 is here, and the delta HF for water is this. What is the delta H for the overall reaction? So we want to do our change in enthalpy is our products minus our reactants. Now the only thing we're going to have to be careful of is coefficients, because this CH3OH at negative 201, for example, is for one CH3OH. But if you take a look here, you don't have one, you have two. Okay. For CO2, they tell you it's 394, but there's two of those at 394. For water, there's 4 of them. Okay. For the oxygen, there are 3 of them. So let's go ahead and start to plug in to our equation. If you want, you can pause it. Maybe you can try it. If you're not unsure about what we're doing, then just go ahead and keep watching. So we have our delta H here. Now we're doing products minus reactants. So this value I have right here is for CO2. Notice I did 2 of them. I'm adding it to 4 of the value for water. So I looked at my value for water. So those are my, if you look, these are my products, because remember, it's products minus reactants. Over on this side, 201 was the CH3OH value, and I did it times 2, because there were 2 of them. And then I had 3 oxygens. Now, you might have looked for oxygen in the problem and not found the value, but they're not going to tell you that elements are 0. You have to know that. And so this was a pure element. This was O2, and it's a pure element, so it's going to be 0 every single time. So then, now it's just a matter of plugging your calculator. Be careful with all those parentheses. Okay, common math mistakes are made on this problem, so just be really careful with that. And you end up with a delta H value of negative 1,354 kilojoules. Okay, and that's really how it works. It's just a plug and chug kind of equation. So you'll be given the delta HFs, plug them in, products minus reactants, use coefficients. Okay, and the unit will come out to be kilojoules, because if you look on your table, or not on your table, but if you look right here, it was kilojoules per mole. But looking at, for example, here, let me get a different pen. Looking at this one here, you had your value, which was in kilojoules per mole. But this coefficient represents moles. So unit-wise, it's like doing moles times kilojoules over moles, and voila, you are left with kilojoules. So your final answer should be in kilojoules. Okay. So that's enthalpy of formation. Now we're going to review the others, and again, you've done these ones before. The next one I have on your paper is bond energies. And in order to use the bond energies, you'd have to be given the bond energies. Okay, you're not expected to know what the bond energy is of every bond out there. But essentially the idea of bond energy is that what we're going to do is take all of the bonds that are being formed and released, and we're going to add up all, or formed and broken, I should say, formed and broken. We're going to add up all the energy it took to form them, we're going to add up all the energy it took to break them, and we're going to see what the difference is, because that's really what the overall enthalpy, overall release of energy is going to be in the problem. But one really important note, and you need to do this some way big on your notes, write yourself a big, huge note, that this one is reactants minus products. Okay, all of the other deltas are P minus R, products minus reactants, but this one is reactants minus products. Okay, it's very important to remember that. So bond energies are reactants minus products. Okay, so let's go ahead and take a look at what something would look like for this. Now this is the problem you have on your paper. Notice the bond energies are given to you on a table. That's usually how they do it. Usually give it on a table like that. Sometimes they'll give you extra ones, by the way, that you don't need. And it says, what is the enthalpy? So remember that little degree symbol is just telling you it's under standard conditions for the following reaction, given the following bond energies. In order to tell what bonds are going to be broken and what bonds are going to be able to be formed, you have to know what your molecules look like. So the very first thing you have to do on these problems is draw the molecule. So we have to go back to good old structure drawing, Lewis structures. So hydrogen, and you're only going to start with drawing one of them, and then you'll have two of them. So I usually do like two, and then I'll put in parentheses what the drawing looks like. Hydrogen only has 2 electrons, so it'll form one quick little bond. Now for oxygen, give myself some space up here. For oxygen, we have 12 electrons to work with. So we do our oxygens, connect them with a single bond. Remember, we filled the octet of one of them, so that's 10 electrons. That would be 12, like so. So we're going to take 2 of these and make a double bond. So now each one of these molecules, what did I miss? 2, 4, 6, 8, 10. Oops. My bad. Forgot to put those on there before I moved. So now both of them are going to end up having 8 electrons, which is what they want. And there's an oxygen-oxygen double bond. So when I draw oxygen-oxygen down here, I need to account for it being a double bond. Okay? And again, we can put our electrons on there. And then product-wise, I have 2 waters. So let's draw water. So water, H2O. So we have 18 electrons to deal with. Oxygen goes in the middle. Hydrogen's on the outside. Connect the outside to the inside with a single bond. Remember, hydrogen can only hold 2. Put the other extras there. Why did I say 18? Seriously? Oh, my bad. I'm really sorry. Rough boarding here. So we have 8 electrons, of course. Hydrogen 1, oxygen 6. So that's a total of 8. And so water looks like that. And so we can draw water in like that. So now you can see all the bonds. Okay, and again, we're going to do reactants minus products. So on the reactant side, I have 2 hydrogen-hydrogen single bonds to break, and I have 1 oxygen-oxygen double bond to break. So let's go ahead and take a look. So here's my 2 hydrogen-hydrogen single bonds. Here's my 1 oxygen-oxygen double bond. And again, I got those values from right over here. And then on this, each water molecule has 2 hydrogen-oxygen single bonds, but I have 2 waters. So you notice I used 4 because I need to break 4 hydrogen-oxygen single bonds. And so that's where those numbers come from. And if I add all of that together, I get negative 481 kilojoules. Again, you accounted for moles, so the mole part of the unit will cancel off, and we'll be left with kilojoules. So that is bond energies. If this method or the next one, Hess's law, is confusing or you can't really remember or this isn't enough of a lesson for you, again, this is review. So you should get out your thermo notebook and spend a little time practicing, maybe looking at the problems from before. If what I'm saying makes sense to you, no worries. We're going to do some more practice. You're going to have some practice after these notes. But if you feel really uncomfortable with these ideas, that might be a good idea. All right, next one is Hess's law. Remember, Hess's law is the manipulation law. Remember, I told you us women love it because we get to manipulate things. And so this is the one where we are given reactions, but they're not necessarily written the exact way we need them to be written. So we either have to reverse reactions, multiply them by a number to get the coefficients right, or leave them alone. And then once we've got them in the right order, then we get to just add the delta H's. So here's the example problem I have in your notes. So our goal is to get the problem to look like this one. Okay, now I taught you a little trick to go through your step equations, which are here, and underline anything that appears in more than one equation. So we have H2 in more than one equation. We have carbon in more than one equation. That's going to help you because you don't want to look at those ones. You want to look at the other ones. So we look at CH4 for the first equation. Notice CH4 is on the product side up here, and it has a coefficient of a 2. Well, in our equation, it's on the product side, but the coefficient's only 1. So we're going to have to multiply this equation times 2. And ultimately, we'll multiply this times 2. Okay? And then let's do the other one, then we'll rewrite them. So that one we're going to multiply by 2. Then, well, actually, let's just go ahead. So multiplied by 2, it looks like this. So there'll be 2 carbons, 4 hydrogens, and 2 CH4s. And then my delta H will be multiplied by 2. So the things you see in red are obviously the new things. Now, in terms of the second equation, C2H6 is a product. C2H6 is a reactant. So we need to reverse this reaction. So I'm going to take what was products and make them reactants, and what was reactants and make them products. I have the right number, so I don't have to change the coefficient. Flip them around. When I flipped them around, notice the sign changed to positive. Okay. Now, once you've done that, it's good practice to double check to make sure you did everything correctly. So you want to add together both of the equations you wrote and see if they do truly give the correct overall equation. And if they don't, then one of your manipulations was incorrect. So 3H2s cancel. Ooh, look at that. 3H2s and 4H2s. So one of those is going to be left. Okay, one of those is going to be left. Look right here. One is left. The 2 C's cancel. And other than that, it looks right. So we have 1 H2, which is what we should have. 2 C2H6s. 1 C2H6 is there. And then 2 CH4s. Okay, so the equation was right, which means we just need to take these values and total them. And when we do so, we get a delta H that's equal to negative 65.3 kilojoules. Okay, so very similar. Not very similar. It's exactly what we did first semester. So again, if you want some more practice with that, I'd go take a look at your notes. We'll do some practice problems, some AP style questions. But if you want more practice just on the basic idea of it, take a look back at your thermo stuff. All right, last one. Save the easiest for last, specific heat capacity. It's a real simple equation, Q equals MC delta T. Q is the amount of heat. Notice the unit though. We've been working in kilojoules. This one's in joules. Okay, so please, please realize that. The mass is in grams. Specific heat capacity can be in joules per gram degree Celsius, or it can be in joules per gram degree Kelvin. So just kind of pay attention to the problem to decide which one it is. If it's given in joules per gram degree Celsius, you can plug the temperature in Celsius. If it's given in joules per gram degree Kelvin, then it needs to be plugged in Kelvin. So pay attention to the specific heat capacity units. And if you remember, there was one that you were supposed to really know, although I'm pretty sure it's written on your equation sheet. We'll take a look. And it's water. Okay, so water is 4.184. And you can either say joules per gram degree Celsius or joules per gram degree Kelvin. That's the same number for both of them, because the size of a Celsius degree and the size of a Kelvin degree are the same. So if we had a problem like the one you have in your notes, they tell you that you are putting in this much heat. I know it's heat because of the joules part, so this is Q. They give you your mass. They give you your initial temperature, and they want us to solve for final temperature. Remember, delta is TF minus TI, always final minus initial, and then they give you the specific heat of the water is 4.184 joules per gram degree Celsius. So we're going to take our Q equals MC delta T. If you want to pause the video, go ahead and plug everything in and solve. See if you can do this correctly. All right, so when you plug it in, you've got your Q plugged in, you've got your mass, 4.184. Notice I left it in Celsius because of that right there was in Celsius. So made it nice and easy. And then I solved, unrounded to get 99.952. We needed to round to 3 sig figs, so 100 degrees Celsius would have been our final answer. So if you have anything to do with specific heat capacity, then this is the equation that you're going to be using. Let me take a look. I've got the equation sheet in front of me. I don't see the specific heat capacity of water on the equation sheet. So I definitely want you to make sure you know it. Probably like in this problem, they'd probably give it to you anyway, but just in case. Okay, so make sure that you do know that equation. In terms of what equations are on the equation sheet, Q equals MC delta T is on there. The enthalpy of formation, the first equation we did, the products minus the reactants, is on there as well. Okay, just so you kind of have an idea, and you have that equation sheet in your notebook to look at. All right, so there is a second video on the rest of the thermo stuff. You can watch that one, at your convenience.